Hello everyone. Today we're going to be talking about Math 100, section 5.3, and this section deals with scientific notation, which is an application of exponents. Now let's read together here for this first block of text, and we're going to fill in a few things, but most of it is just going to be reading. So first, numbers occurring in science are oftentimes extremely large or extremely small. Think universal scale or, atoms and molecules scale. Because of the difficulty of working with many zeros, scientists often express such numbers with exponents using a form called scientific notation. In scientific notation, there's always one non-zero digit before the decimal point. So, for example, 1.72 has one non-zero digit before the decimal point, whereas 14.9, that has two non-zero digits, right? So this is no dice. Same for maybe 0.95. That has a zero before it has to have one non-zero decimal place. So, a number is written in scientific notation when it's expressed in the form a times 10 to some power. Now remember, a has to be 1 included, but smaller than 10, right? It can be any number between 1 and 10, with 1 being included but 10 not being included, right? Because it has one non-zero decimal place. So A could be something like 5.64, but could not be something like 25.7, because that has two digits. That's bigger than 10, right? It has to be between 1 and 10. 1 is okay, though. So this is no dice. Now, writing a number in scientific notation. First, we reposition the decimal point. The number will already have a decimal point. Every number has a decimal point. We'll place some type of symbol. The book uses the caret sign to the right of the first non-zero digits. This is where our final decimal point will be placed. Once we move it, that's where it will end up. So we place an arrow. Then we determine the numeral for the exponent. To do this, we count how many digits we moved from the original decimal point to the caret symbol. This number gives the absolute value of the exponent on the 10. We don't know if it'll be positive or negative. So if we get 7, it could be positive 7 or negative 7. Step 3 tells us about the sign. So to determine the sign for the exponent, we do this by deciding whether multiplying by 10 to the n should make the result of step 1 greater or less. The exponent should be positive to make the result greater. The exponent should be negative to make the result less. So let's look at our first number, 153,000,000,000,000. The decimal place in this number is currently right here at the end, right? There was no decimal, it's a whole number, so it's hiding right here. Reading this number, the first non-zero digit is 1. So I'm going to put a little arrow here. That's where my new decimal point will lie. Now, how do I get from here to there? Well, I count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So there was 11 hops. Now, my new number will be 1, the decimal is now here, 0.53. Everything else is zeros, so you don't need to write them, times 10, and it's either going to be positive 11 or negative 11. My question is, 1.53, do I need to make it bigger to get to this number or smaller? I need to make it bigger, right? So my exponent will be positive to make it bigger. So 1.53 times 10 to the 11 is the same as 153 billion. We rewrote the number in scientific notation. Let's look at our next example. We have 9,547.3. Now, the new decimal place will go to the right of the first non-zero digit. 9 is the first non-zero digit. So it'll be right here. To get from here to there, I hop 1, 2, 3 times. So my new number will be 9.547. Notice I had to write all the decimals. There were no hidden zeros I could drop off, right? Everything here was a non-zero digit. Times 10 to the, it's either going to be positive 3 or negative 3. To make 9.5 into 9,500 something, I need to make it bigger, so this will be positive 3. So 9.5473 times 10 to the third is the same number as 9,547.3. How about really small numbers? Both those were big numbers. What about small numbers? Let's look at 0.00. So let's write it. 0.000. 1, 2, 3, 4, 5, 6. There's 7 zeros. So we got 7 zeros there. 5, 8, 4, 2. Reading left to right, the first non-zero digit is this 5. So I'm going to put the new decimal to the right of it, which is 1, 2, 3, 4, 5, 6, 7, 8 hops. So my new answer, my new number will be 5.842 times 10 to the, and it's going to be either positive 1, 2, 3, 4, 5, 6, 7, 8, positive 8 or negative 8. My question is, do I need to make this number smaller or bigger? Well, a lot smaller, right? So it'll be negative 8, because I need to make 5.8 smaller to make it this size, right? Now, 6.1134, 6.1134, this number already has the decimal place in the correct position. So, if I want to put it in scientific notation, I'll multiply by 10 to the 0. I move the decimal place 0 spots. So I'll leave it 10 to the 0. Remember, what's 10 to the 0 really? It's the number 1, right? 1 times anything keeps it the same. Seems weird to write this number like this, but that is that number in scientific notation. Now how about in reverse? 4.125 times 10 to the 5th. Well, 10 to the 5th tells me to make this number bigger. So I take 4.125 and I make it bigger. How much bigger? 5 hops. 1, 2, 3, 4, 5. My new decimal place is right here. Now, what goes in the hops here? There's no number here. You fill in zeros. Somebody once described it to me as you put a Cheerio in the bowl. If you like cereal, that might help you remember. So my new answer is 412,500. The decimal place would be here. I can put a comma if I want. But 4.125 times 10 to the 5th is the same as 412,500. Now, same thing here. 1.456 times 10 to the negative 4. The negative tells me I make this number smaller. How much smaller? 4 hops. 1, 2, 3, 4. The new decimal will be right there. Once again, we fill in zeros, which you can also put out front of a decimal, right? So our new value becomes 0.001456. We made it smaller, right? Because the exponent was negative. And we fill in the placeholder zeros. We put Cheerios in the bowl. So that's scientific notation. We can also do math with scientific notation. And so for this first example, we can look at the whole number portions, the parts here, and the tens. 8 times 3 is 24 times 10 to the... Remember, when you multiply two things, you add their exponents. So I'll take 6 plus negative 4 as the power on the 10. This becomes 24 times 10 to the second. But I need to be careful. This is not in scientific notation because the decimal is currently right here, but it needs to be here, right? 24 is bigger than 10. It has to be a number between 1 and 10. So I need to move 1 hop to the left, which gives me 2.4 times 10 to the... I need to make this number bigger to get to 24, so I'll add 1 here. It'll be 10 to the third, right? Which, if I undo, move it 3 hops right, it would be 2400 in standard notation, right? Now, same thing here. 9 divided by 3 is 3 times 10 to the 5 minus 7. The quotient rule, you subtract exponents. This would become 3 times 10 to the minus 2. Right? 5 minus 7 is minus 2. So to remove it from standard notation, or from scientific notation to put it in standard notation, it would be 0.03, right? I would take the decimal place that's right here and hop 2 spaces left. -2 tells you to hop to the left to make the number smaller. We won't be doing much with calculations. I just wanted us to be aware we can. The important thing from this chapter is converting back and forth, like in the first sets of examples, from the first and second page. Converting to scientific notation and converting back from scientific notation. And that's it. Short, sweet section, right? 5.3, scientific notation. I will see everybody next time.